Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Riding sunlight, the journey of solar sails. In the realm of space exploration, the concept of solar sails has captivated scientists and visionaries alike for decades. Harnessing the power of sunlight to propel spacecraft, solar sails promise a revolutionary method of travel that requires no fuel, potentially enabling missions to the farthest reaches of our solar system and beyond. This narrative delves into the history, principles, advancements, and future potential of solar sails, highlighting their transformative impact on space exploration. The idea of using sunlight for propulsion dates back to the early 20th century when the Russian scientist Konstantin Tsiolkovsky, one of the founding figures of astronautics, proposed the concept. Tsiolkovsky theorized that pressure from sunlight could be harnessed to propel a spacecraft equipped with large, reflective surfaces. This notion was later expanded upon by Soviet engineer Friedrich Zander, who envisioned solar sails as a practical means of interplanetary travel. Despite these early musings, the technology required to realize solar sails was not yet available, and the concept remained largely theoretical for many years. The principle behind solar sails is relatively straightforward yet profoundly ingenious. Solar sails rely on the momentum transfer from photons, the elementary particles of light, when they strike a reflective surface. Although photons have no mass, they possess momentum, and when they collide with a surface, they impart a tiny amount of force. By deploying a large, lightweight sail made of highly reflective material, a spacecraft can capture this momentum and generate continuous thrust. This thrust is minuscule compared to conventional rocket engines, but it accumulates over time, allowing a solar sail-powered spacecraft to reach significant speeds. One of the first practical demonstrations of solar sailing came in the form of the Japanese spacecraft Ikaros, interplanetary kitecraft accelerated by radiation of the sun. Launched in 2010 by the Japan Aerospace Exploration Agency, JAXA, Ikaros was the first spacecraft to successfully demonstrate solar sail technology in interplanetary space. The spacecraft deployed a 14-meter-wide sail made of a thin, reflective membrane and used the pressure of sunlight to propel itself. Ikaros not only validated the concept of solar sailing but also demonstrated the potential for controlling the sail's orientation to navigate through space. Building on the success of Ikaros, various space agencies and organizations have continued to explore and advance solar sail technology. The Planetary Society, a non-profit organization dedicated to space exploration, launched its own solar sail mission, LightSail 1, in 2015. Funded through a crowdfunding campaign, LightSail 1 aimed to demonstrate the feasibility of solar sailing in Earth orbit. Although the mission faced some technical challenges, it successfully deployed its sail and provided valuable data for future missions. This was followed by LightSail 2, launched in 2019, which successfully demonstrated controlled solar sailing in Earth orbit and achieved significant public engagement and support for the technology. Solar sails offer several advantages over conventional propulsion systems. One of the most significant benefits is the elimination of the need for onboard fuel, which drastically reduces the mass of the spacecraft and allows for longer duration missions. Traditional rockets carry a finite amount of fuel, limiting their operational lifespan and range. In contrast, solar sails can continue to accelerate as long as they receive sunlight, making them ideal for missions to distant destinations where carrying large amounts of fuel would be impractical. The continuous thrust provided by solar sails also enables trajectories that are not possible with conventional propulsion. For example, a solar sail-powered spacecraft can gradually spiral outwards from the Sun, gaining velocity over time and reaching higher speeds than a rocket that relies on a brief burst of thrust. This capability opens up new possibilities for exploring the outer regions of the solar system and beyond. In particular, solar sails are well suited for missions to the Kuiper Belt, the Oort cloud, and even interstellar space. Despite their potential, solar sails also face several challenges that must be addressed to fully realize their capabilities. One of the primary technical hurdles is the development of lightweight, durable sail materials that can withstand the harsh conditions of space. The sail must be both highly reflective and resistant to degradation from solar radiation and micrometeoroid impacts. Advances in materials science have led to the creation of ultra-thin, lightweight films made from materials such as mylar and captain, which are used in current solar sail designs. Researchers are also exploring the use of advanced materials like graphene, which could offer even greater strength and reflectivity. Another challenge is the deployment and control of the sail. Solar sails must be precisely oriented to optimize the thrust generated by sunlight, requiring sophisticated attitude control systems. This can be achieved through the use of small thrusters, reaction wheels, or by varying the reflectivity of different parts of the sail. The deployment of the sail itself is a critical and complex operation, as the sail must be carefully unfurled from a compact stowed configuration without becoming tangled or damaged. Successful deployment mechanisms have been demonstrated in missions like Icaros and LightSail, providing valuable experience for future projects. Looking ahead, solar sails hold immense potential for a wide range of space missions. One of the most exciting possibilities is their use in interstellar exploration. The Breakthrough Starshot Initiative, announced in 2016, aims to send a fleet of small, lightweight probes to the nearest star system, Alpha Centauri, using powerful ground-based lasers to propel them at a significant fraction of the speed of light. These probes would be equipped with tiny solar sails, enabling them to reach Alpha Centauri in just a few decades. While this ambitious project presents numerous technical challenges, it highlights the potential of solar sails for pushing the boundaries of human exploration. In the realm of planetary science, solar sails could enable missions to study distant asteroids, comets, and other small bodies in the solar system. The continuous thrust provided by solar sails would allow spacecraft to rendezvous with and study multiple targets over the course of a single mission, providing valuable insights into the composition and dynamics of these objects. Additionally, solar sails could be used for long-duration missions to the outer planets and their moons, where the ability to generate thrust without relying on onboard fuel would be particularly advantageous. Solar sails also offer potential benefits for Earth science and space weather monitoring. A solar sail-equipped spacecraft could be positioned at strategic locations in space, such as the Lagrange points, to provide continuous observations of the Sun and the Earth's magnetosphere. This could improve our understanding of solar activity and its impact on space weather, which is critical for protecting satellites, power grids, and other infrastructure from solar storms. In the context of human space exploration, solar sails could play a role in supporting missions to Mars and beyond. While solar sails alone may not provide sufficient thrust for crewed missions, they could be used in conjunction with other propulsion systems to reduce the overall fuel requirements and extend the mission duration. For example, solar sails could be used to transport cargo and supplies to Mars ahead of a crewed mission, reducing the need for heavy lift rockets and enabling a more sustainable approach to interplanetary exploration. The development of solar sail technology has also spurred innovation in related areas, such as space robotics and autonomous navigation. Solar sail missions often require advanced robotics to deploy and control the sail, as well as autonomous systems to navigate and make real-time adjustments based on the spacecraft's orientation and trajectory. These technologies have broader applications in space exploration, including the development of autonomous spacecraft for deep space missions and the use of robotics for assembling and maintaining space habitats. As the technology continues to mature, international collaboration and partnerships will be essential to advancing the capabilities and applications of solar sails. Organizations like NASA, JAXA, the European Space Agency, ESA, and private entities such as the Planetary Society have already made significant contributions to the field. Continued cooperation and sharing of knowledge and resources will be crucial for overcoming the technical challenges and realizing the full potential of solar sails. In conclusion, solar sails represent a transformative technology with the potential to revolutionize space exploration. By harnessing the power of sunlight, solar sails offer a sustainable and efficient means of propulsion that could enable missions to the farthest reaches of our solar system and beyond. While significant challenges remain, the progress made to date demonstrates the feasibility and promise of this innovative approach. As we continue to push the boundaries of human exploration, solar sails will undoubtedly play a key role in our journey to the stars, unlocking new frontiers and expanding our understanding of the universe.